All right, so this is part 13 of our Unit 1 videos, and this is the last video in this part. So we're going to finish up pages 38 and 39 here. We're going to be looking at the algebra of functions and function composition. The first couple of examples we're going to do here will probably seem like kind of like review, stuff you've done before. We're just adding functions together, subtracting them, multiplying them, and dividing them. We will talk a little bit about domain issues here, where what our denominator can't equal or inside a square root, things like that. But then we're going to be moving on to function composition, and I'm hoping to ease you into that a little bit. It is a newer topic, but it's something that's really important for the rest of the semester. And for those of you moving on to calculus after this, it'll be really crucial for that as well. So, first thing we're going to look at is excluded values. And these are values that we cannot plug into a function because they would make the function undefined. So things like having negatives inside of square root, or if we have a fraction, make something that would make our denominator 0. So in this case, it's asking us to state the domain. Now the first thing I notice is that x cannot equal 7, because if it equaled 7, that would make our denominator 0. But this is not the domain. The domain is what x can equal. And x can equal everything except for 7. So my domain would be negative infinity to 7, a parenthesis, since it does not equal 7, and then from 7 to infinity. Okay? So make sure you actually state what the domain is, what x can equal, not what it can't equal. Now this next part here is just really a notation thing. Here, the sum of two functions, f of x plus g of x, and then combining like terms. But you might see it written like this. Okay, so it might be written like this, but it essentially just means add those two functions together. Similarly, subtraction, multiplication, and division. And again, this is where we want to be careful that our denominator doesn't equal 0. So let's look at a couple examples. Here we have f of x, g of x, and h of x. And we want to find f minus g. So f of x is x squared minus 3 minus, and I'm going to put parentheses around g of x because that minus sign needs to be applied to the whole function. So that'll give me x squared minus 3 minus 7x plus 5 when we distribute that minus sign. Combining like terms, that gives me x squared minus 7x plus 2. Okay. The next one is g times h, so we want to multiply them. G is 7x minus 5, and h is 2x plus 1. You can use FOIL or you can use a box, whichever you prefer. I'm going to go ahead and do a box really quickly here. We have 2x plus 1 and 7x minus 5. That's 14x squared, 7x, 7x, negative 5, and then negative 10x. Combining like terms, 14x squared, 7x, and negative 10x is negative 3x minus 5. So you're seeing our answers here are not numbers, but expressions. This next one says h over f. So h of x is 2x plus 1. F of x is x squared minus 3. But we want to be careful and state what x cannot equal. So if you set your denominator equal to 0, that will tell you what x cannot equal. So I can add 3 over, square root both sides, plus or minus sign. X cannot equal plus or minus the square root of 3. So we want to make sure that that's clear with our answer. So that's the algebra of functions. We're going to look now at function composition, and this is plugging a function into another function. So to ease kind of us into this, I'm going to add something that's not actually in our notes. Let me use some scratch paper here real quick. Now, if you recall back to what we were doing even just a video or so ago, and if I had, let's say, a function f of x equals 3x minus 5. and I said, let's find f of 2. That just meant plug in 2. Well, 3 times 2 is 6. 6 minus 5 is 1. If I said, let's find f of a, that means the same thing. I'm just plugging in a for x. And that would just be my answer. It would be an expression like that. Now, notice I didn't leave an x there. I replaced x with a. So this is the original function, and I'm saying find these values. Now, what if I said find f of 2a? Well, same thing. We're just plugging into a where there was an x. And that would simplify to 6a minus 5. We could also say let's find f of a plus 1. Okay, so 3a plus 1 minus 5. That'll be 3a plus 3 minus 5. That gives us 3a minus 2. And I could keep going. I could keep just coming up with more and more functions that we're plugging in here. Now, what if I said, okay, f of x equals this function here, and let's let g of x equal 2x plus 1. Okay. If I said I want to find f of g of x, all that means is plugging in g of x, which is 2x plus 1. Well, f is 3x minus 5. I'm plugging in 2x plus 1. Distributing, I get 6x plus 3 minus 5, and that's 6x minus 2. Okay. That's what we're doing. This is called function composition, and I just kind of gradually brought us to plugging in a function, but this is the notation that we're going to see where we're plugging a function into another function. Now notice in that original function, f of x, 3x minus 5, I did not keep that x there. The x got replaced with parentheses, and we plugged in this inside function. So that's what we're going to be doing here. Now, there's two ways to write this, f of g of x, which is what I was just using, but the other way you could see it is f of g of x. That's what this notation here is. This is an open dot, f of g of x. These mean the exact same thing. G is on the inside of f. G of x inside f of x. When we're talking about the domain of these functions, there's two things we need to consider. The domain of the inside and the domain of the answer. Okay. So here we have f of x and g of x, and we're going to find f of g of x, which again means the same thing here. And I like to color code these. You're welcome to do the same, or you're welcome to just write it all in the same color. It doesn't matter to me. So f of x is 3x minus 4. Notice I did not write the x. The x is being replaced with parentheses, and we're plugging in g of x, which is x squared minus 2x plus 6. From there, it's just simplifying. Distributing my 3 here, I get 3x squared minus 6x plus 18 minus 4, which simplifies to 3x squared minus 6x plus 14. That's my answer. Now, we just did f of g of x, but we could also do g of f of x and make g the outside function. All right, so g being the outside function, x, again, we're replacing x with parentheses, squared, minus 2. And if you have another x, it's just another set of parentheses. I did not write an x. I did not write an x. We're replacing those x's with parentheses so that we can plug in our inside function, f of x. That's the hardest part here, is making sure that you've got that correct. Now 3x minus 4 squared, Well, you can either use FOIL or you could use the box method, whichever you prefer, but you're not just putting the square on each of these terms, you're multiplying that out. And if you use the box method or you use FOIL, you'll get 9x squared minus 24x plus 16. Then here, distributing the 2, we get minus 6x plus 8, and then plus 6. Combining like terms, we have 9x squared. We have a negative 24x and a negative 6x. That's negative 30x. And then we have 16 plus 8 plus 6 is plus 30. Now the next example says g of f of 1. Well, we just found g of f of x. If we're plugging in 1, then that's just plugging in 1 to x here. 9x squared minus 30x plus 30, and we're plugging in 1 for x. So plugging in 1 squared is 1 times 9 is 9. 30 times 1 is 30 plus 30. Those cancel and we're left with 9. Now there is another option. If you had not already had this answer from the previous question to just borrow, then what you could do is find g of f of 1. This is separate from that question, so let me make that clear there. Well, the first thing I want to find then is f of 1. And f of 1, well, f of x is 3x minus 4. We're plugging in 1. 3 times 1 is 3, minus 4 is negative 1. And that means that this is equal to this. So I can replace it. Instead of f of 1, I can write negative 1. So g of negative 1. Well, g of negative 1 is plugging in negative 1 to this function. Negative 1 squared minus 2 times negative 1 plus 6. Negative 1 squared is 1. Negative 2 times 1 is plus 2 plus 6. And 1 plus 2 plus 6 is 9. Gives us the exact same answer, 2 different ways. Now there's one last thing we are going to look at in this last part here. Well, actually, really two last things here. This next example has us go the opposite direction. Oh, I take that back. That's not what we're doing quite yet. So here we have f of x, g of x, and we want to find f of g of x, and we want to state the domain. So this is where we're going to see the issue that we just talked about, where we might have a domain issue. And especially with fractions, we know we can never divide by 0. So we want to find f of g of x. So f is the outside, g is the inside. And if you recall back to the top of the page, we want to make sure we're looking at the domain of the inside and the domain of the answer. So my inside function is g, and g is 3 over x. Well, we know x cannot equal 0 then. I'm going to put that off to the side here. So x cannot equal 0. And then we will come back to when we get our final answer to see what restrictions we might have there. So f is our outside function. So let me go ahead and write this again. F of g of x. And f is 2 over x minus 1. Okay. So for x, I'm plugging in my inside function 3 over x. Well, in order to simplify this, I need a common denominator here. So I'm going to multiply x by, or I'm going to multiply 1 by x over x, and that'll give me a common denominator here. So I have 2 over, and I have a common denominator of x, and on top I have 3 minus x. 1 times x is just x. Well, remember when we divide fractions or when we have a complex fraction, we can flip the bottom one and change it to multiplication. So this becomes 2, or in other words, 2 over 1 times the reciprocal, so x over 3 minus x. That becomes 2x over 3 minus x, and that's f of g of x. So we found that, but we need to look at this. The x value that would make the denominator 0 here is 3. So we have these two pieces, x cannot equal 3 and x cannot equal 0. And those inform our domain. So my domain is everything except for those values. Now, even though it doesn't ask me to graph, I think this is a helpful visual. If you think about a number line and you think about 0 and 3, x cannot equal those values, so I'm going to put an open dot there. But it can equal everything else. And if I was going to write the domain of this number line here, it would be negative infinity all the way to 0. And then from 0 to 3, not including 0, so no brackets. And then open dot 3 to infinity. So it takes 3 intervals for me to state the domain of this function here. Okay. One last example, and then we are done with Unit 1. This last topic is called finding the difference quotient, and when you get to calculus, this will be one of the first topics you see. A difference quotient, in calculus, you'll talk about it in regards to the concept of limits. We won't get into that quite yet here. We will just practice finding the difference quotient. And the formula for the difference quotient is f of x plus h minus f of x over h. And again, we're not going to worry too much at this point about what this means. You do need to know this formula here, so make sure that you know it. But we will just practice finding the difference quotient at this point. So what I suggest first, we know f of x. Let's find f of x plus h. So I'm just going to plug in x plus h where there was an x. And that's equal to negative 3x, negative 3h plus 5. And so I can just go ahead and plug into this formula now. F of x plus h is negative 3x minus 3h plus 5 minus f of x all over h. Well, when I simplify that numerator there, I have negative 3x minus 3h plus 5. A negative times a negative will become plus 3x, and a negative times the 5 will be minus 5 all over h. Well, we can see here that a number of things cancel out. Positive 3x and negative 3x, those cancel. Positive 5 and negative 5, those cancel. And at this point, all I have left on top is negative 3h over h. Well, in this case, the h's can reduce, and we're just left with negative 3. So in this case, my difference quotient is negative 3. Again, we're not talking about the meaning of difference quotient at this point, but just practicing finding it. And that brings us to the end of Part 13 and all of Unit 1.